All right, ladies and gentlemen, I'm compelled to tell you, class recording has begun. So anything stupid that you say will now be recorded for all people on the internet to hear, if they so choose to watch this video class recording, which you might not care about their opinion if they choose to watch this recording, on their own. So, Vortex Lord, Vortex. Watch your language for Vortex Lord. All right. So, all right. Yesterday, I know you better watch this when we get home. So. All right, yesterday we began discussing the kinematic equations. The whole gist of yesterday was, now that we've introduced all of these concepts, displacement, velocity, acceleration, how time fits into all of this, what we want to do now is mathematically come up with representation of how these things are all related. If an object is accelerating for a certain amount of time, how far does it go during that time? If it accelerates for a certain amount of time, how fast is it going at the end of that time? So the kinematic equations are relationships between displacement, velocity, acceleration, and time. But they are only valid, too far. They are only valid when the acceleration that that object experiences is a uniform or a constant acceleration. Sometimes that acceleration could be zero. That could be a constant acceleration. But generally, especially when we're starting off talking about one-dimensional motion, we're talking about an object that is speeding up or slowing down, and then at a constant rate, a uniform acceleration. So we're looking at mathematically representing the relationship between displacement and acceleration and velocity and time. But these relationships only hold true when that acceleration is a constant value. All right, good there? We are going to skip to the end, or the end, close to the end, and look at this chart. This chart is a summary of the 4 kinematic equations. We got through 3 of them yesterday in class. The one at the bottom is kind of hard to show you how it's all derived, but it also fits into this category. So this chart is going to be a good reference page for you, especially when we're starting off, when we're looking at analyzing a problem, determining what the problem is asking us for, what's in there to work with, and then how are we going to get to the information that we need. Like I said, this chart would be a good reference as we're doing these problems to know the equations so you can go back, check them out, et cetera, et cetera, et cetera. They're all on the sheet that I gave you yesterday, but here they're nice and all together. One thing that should become obvious in a little bit when we start doing problems is the fact that there are only 4 variables in each of those equations. A big part of doing problems using kinematic equations is determining which of the equations is the appropriate one for us to use based on what we're looking for and what they gave us to work with in the problem. And we'll talk about how to do that here in just a second. So each equation has 4 variables, and that means that our magic number really is 3. We have to know 3 pieces of information about the motion that we're trying to analyze in order to find a 4th one. And then how we find that 4th one is dictated by, well, which equation are we going to use? And we'll figure that out here in just a second. Here's a summary of the 4 kinematic equations, the 4 relationships, the 4 equations that relate displacement, velocity, acceleration, and time for a uniformly accelerating object. All right, good there? Do we need another second here? While we're waiting, if you haven't done so, we are going to start on page R37, which is way in the back of your book. It's Appendix B in the back of your book. So R37 if you're not there. Yeah, for some of the problems. So a lot of those answers are just like the number answers, you know. So like when I post things online, I'm going to give you like the work and stuff like that, but the answers are back there. So, all right. On page R37, we are going to start off. First, I have to do this. We are going to start off looking at problem number 137. And I don't have my, stand by, forgot to pull that up, whoa. All right, let's move that down just a little bit, okay. So, let's move that down here, goodness gracious. Wow, glad everybody gets to see this. Okay, so, like I said before, this is page R37, which is in the back of your book. Number 137. So it says, a skateboarder starts from rest and accelerates down a ramp with a constant acceleration of 2.1 meters per second squared. It says, what is the speed of the skateboarder 2.5 seconds after she starts? So, starting off, and we should do this with every problem, not just kinematic equation problems, but every problem. What is this problem asking us for? What does it want us to solve for? Speed, right? Because it says, what is the speed, right? But if we look a little bit deeper, which speed? Because if you look at those equations, there's actually two velocities, right? Which velocity is this one actually asking us to solve for?
The final speed.
Because it says, what is the speed after, right? So that means that V final is our unknown value in this problem. That's what we're looking to solve for. Now that we know what to solve for, let's take a look and figure out what else the problem has for us to work with. So what are some other things that this problem is telling us about this motion? Things we know.
She starts from rest.
Okay, so she starts from rest. Sam, what is that going to give us? Which variable is that going to give us?
Is it the V initial?
That's going to be V initial. So V initial, if she starts from rest, is equal to 0 meters per second. Okay? So that's one thing we know about this skateboarder's motion. What's another thing that we know about this skateboarder's motion?
Acceleration.
Okay, it tells us that there is a constant acceleration of 2.1 meters per second squared. So that means that we know the acceleration of this motion is 2.1 meters per second squared. What else did they give us to work with in this problem? Okay, they give us the time, right? That this is 2.5 seconds of skateboarding. Okay? So, 3 pieces of information, we're looking for a fourth. We said that each one of those kinematic equations has 4 variables in it. So if we know 3 of them, there should be an equation for us to use to get the 4th. So you check your charts, right? And you find the equation that has these 4 variables in it. And if you look, it looks like this. That's the equation that contains the 1 variable that we're looking for and the 3 that we already know. It's important that the one we're looking for is in there because that's what we have to solve for, right? So now it's a matter of plugging in things into the right spot. We don't know VF. That's still going to be our unknown. We know that the initial velocity is equal to 0 because that's starting from rest. Plus, the acceleration that they gave us was 2.1 meters per second squared. And then it says that this time is 2.5 seconds. Okay? So solving this one for VF is pretty easy, right? Take it, and I believe when your calculator gives it to you, it's 5.25. Is that right? Okay. So 5.25, but 2 significant digits here, right? 2 significant digits in the time, so we should round that one probably to 5.3 meters per second. Okay? Good there? Okay. I'm not going to require that you do every problem in this fashion. But when I do examples in class, I'm going to do it this way because I think it's a good step-by-step orderly fashion to getting you to where you need to get to. If you see it faster, if you pick out things out of the equation faster, you're like, oh, that means I have to use this equation, that's fine. You can do it that way. If you're getting the right answer, I don't care. But for now, I'm going to do it this way just to make sure we kind of go step by step and hit all the highlights. Okay? Good there? All right. Let's continue on, and let's take a look at problem number 139 on that same page. So 139 on that same page says, this is, again, page R37. It says, a horse is running with a speed of 4.6 meters per second. If the horse comes to rest in 15 meters, what is the magnitude of its acceleration? So, first things first, what is this question asking us for? The magnitude of acceleration, right? That's what this thing is asking us for. So A is our question mark in this problem, right? Things we have to work with. What did they tell us about in this problem?
Speed.
Okay, which speed, Sam?
I don't know.
Okay, well, let's talk about that, right? No. Because what does it tell us is happening to the horse in this problem?
It
Comes
comes to rest.
to rest, right?
At the beginnings?
No, because if it comes to rest, what does that mean ultimately this horse is going to be doing? Slowing down and eventually what? Stopping, right? So what piece of information is that going to give us? What does V final have to be here? It's got to be 0, right? Because it comes to rest. Pardon my sitting down. It's hard to write when I'm standing up and turning around like this. So, and I'm on the video. You won't see me sitting down, so nobody needs to know.
But
Right?
now
Foiled Sams. All right. Other pieces of information that we have here in order to work with this problem. What else did they give us to work with?
Minutes of time?
Okay, that's not a minute. What is that?
Oh.
That's a meters, right? So, if something is measured in meters, which variable is that? What's the only one of those 5 variables that's measured in meters? The displacement, right, of that horse over this time is 15 meters. Okay? What else? What else did they give us to work with? Which speed, Jamie? Now this one's a little different. It says that the horse is running with this speed, but eventually what happens to the horse? It comes to rest, right? So which speed is this going to be? That's going to be the initial speed, right? So V initial is equal to 4.6 meters per second. I don't know, we'll have to go back and check the tape, I guess. All right. So we said when working with our kinematic equations, the magic number in terms of things we need to know is what? 3. Got to know 3 things. And we know 3 things. So now it's a matter of going back to the list of our equations and finding the equation that has the 3 things that we know, plus the one thing that we're looking for, because that one has to be in the equation. So, going back to the list of equations, the one that has the three things we know and the one thing we're looking for looks like this. Okay. Vf squared equals Vi squared plus 2 times A times delta X. Okay. Good there? So now we start plugging in things we know. The final velocity in this problem we figured out was going to be 0, so we plug that in there. The initial velocity of this horse, we said because it was running with a speed of 4.6, means 4.6 goes in that spot there. Plus 2 isn't a variable. It's part of that equation. So that just stays. We can't do anything about that. But next, right, we don't know what the acceleration is. We're trying to solve for that. But we do know that the displacement is 15 meters. Okay? So now it's just a matter of doing algebra and getting A by itself. There's lots of different ways you can do this. I really don't care how you do it, as long as you get A by itself. Okay? So, what's the first thing we could do here? Like I said, you don't have to do it this way. Square 4.6, right? Technically we have to square 0 as well, but it's pretty easy, right? So we could square 4.6, right? Also, this term right here, 2 times A times delta X. Because it's multiplication, does it matter what order we do it in? No, right? And once again, you don't have to show me this every time, but just in case, right? So that leaves us with 0 equals, Jamie, did you square 4.6?
Yeah,
21.62. Okay, 21.62.
16.
Oh, 16. Okay, 21.616 plus, and then I would multiply 2 and 15 first to leave us with 30A. Right? Okay. And then it's just a matter of getting A by itself. So first thing you do, right? Subtract 21.16, and again, you do not need to show me this every time, okay? Just because this is the first time we've done this, I want to make sure we're doing our algebra right. The 21.16 from both sides, right? Then what are you going to do? Then divide by 30, right? So that leaves us with an acceleration of 0.7. Okay. Is there more than that, or is that just? Okay. Okay.
Was it negative?
Okay, well, so let's talk about why it's negative. First, it's negative because we subtract this negative over here, right? But more importantly, in terms of the motion of this motion, what is this horse doing? If it ends up at 0, physically that horse is doing what? Slowing down, right? So we should end up with a negative value, okay? 2 sig digs in 15, 2 sig digs in 4.6. Don't worry about the 0, that doesn't count. So we should round this to negative 0.71 meters per second squared. Is that the answer to this problem? Technically, no, because what did the question only ask us for? What is the magnitude? So technically, the answer to this question is just 0.71. But part of the whole idea with the kinematic equations is it should give us direction. Okay? All right. On the calendar for tonight, there are several homework problems that deal with these kinematic equations. You don't have to do them all. Do as many as you feel comfortable doing to feel confident that you can do these problems, okay? There are 11 of them listed. They use all 4 of the different equations. You should use at least one time, okay? Answers are posted right here, right? So you can go back and check and see how you're doing, okay? On Thursday, we will review a little bit at the beginning. Then I will give you time in class to continue working on the lab that we started last week that we didn't finish, okay? So that's our plan for Thursday. Okay?